Welcome back to ECE 220. Tomorrow we are going to begin RLC circuits, which means now we have two energy storage devices. But before we get there, we want to talk about switching before infinity, whatever that means, and look at a circuit that involves a negative resistor and what does that result in. And now we'll see that we actually have unbounded responses, where in the past we've had these nice exponential decay responses with negative resistance. Then we can have just the opposite of what we've been having all along. RLC circuits are chapter 8. That's the next to the last chapter for this class. We'll be getting as far as chapter 9 in 220. So just as a preview, Group B, you have your lab today. That's the last section in the sequence of sections for this class. Homework 9 is also due today, and that's the last piece of material that will be on exam number 3. We will have an exam review session here in class on Monday, and Friday we will not have class. So I'm telling you that out of order, but this Friday we don't have a class. Then the following Monday will be a review session for exam number 3. After your exam, which is next Thursday, you won't have to come to class that Friday. So you're having the next 2 Fridays off at least, and that gives Group A a chance to do their pre-lab, which is due on Saturday. So your pre-lab for lab number 4 is due on Saturday, and I think I've given all of the announcements that are now listed on the screen. We want to go through a couple of examples today, as I previewed before. One is relative to switching. Last time we did introduce switches, but we actually allowed our exponential response to reach its final state or its final location. Today we want to switch before we get to infinity, and here infinity in quotes is 5 time constants. What happens when we switch before we get to our final value, which we're assuming approximately is 5 tau, which gets us within 1% of where we're going or where we started from, and we'll do an example with an unbounded response where we actually have a effective resistance that's negative. Here's our example for switching before infinity. That just sounds so dramatic. So switching before infinity, or it's really switching without reaching 5 tau. That doesn't sound so inspiring. So you can now say switching before infinity, switching before we've reached infinity. It really means switching before we've reached this 5 time constant time interval. And tau depends obviously on where that switch is located. Here, I've created this circuit to have 3 different switch positions, and we want to find the voltage across that 1/2 farad capacitor. The switches are, we're going to just do a sequence. We'll be in position A for time less than 0. Then we'll switch and put the switch in position B at time 1/2. No, at time 0. And then at time 1/2, we will switch from position B to position C. We'll be in position C from 1/2 all the rest of the time. We're switching then between A, B, and C. We're starting in A at time less than 0. We will then transition to B at time 0 and stay there for 1/2 second. And then at that time, we will switch to position C. Is it clear what we're doing with the switches? We're just switching clockwise, A to B to C. We start in A, go to B, and then we go to C. And hopefully you can grasp that we have 3 different configurations of the circuit based on where that switch is located, A, B, or C. And we want to find what does the voltage across that capacitor look like from time 0 all the way up to infinity in the actual case of infinity. Now I'm hoping you have that circuit digested, and we want to now understand, or at least determine, what is this capacitor voltage from minus infinity up to 0. What does this capacitor voltage look like with switch in position A? And don't you wish the exam question was that easy? A, B, C, or D, or E? What is the answer here? What's the voltage across that capacitor at time 0? If we're starting in position A. It's at 0, correct? We're just shorting out whatever charge was on that capacitor to the reference node or to common. So now we can say that we're starting at 0 volts for t less than 0. And what do we know about capacitor voltage? Or what do we know about capacitor current? Are any of those special? Are any of those variables special based on what we've been talking about? And ICE, if that gives us any help. One of those variables is special. And it's the voltage, because that's the state variable. So let's just remind ourselves of that. The capacitor voltage is a state variable. What does that mean? What does that give us? The fact that it's a state variable, does that tell us any more useful information about how this voltage behaves at different, let's say, points of time? Before or after a switch, for example. What's the voltage like? The voltage is continuous, so we now have capacitor voltage is a state variable and remains continuous. Which now allows us to say, or that is, V sub C of 0 minus is going to be the same as V sub C on the right side of that point in time 0, or V sub C of 0 plus, and we've just determined that that's 0 volts. What's now going to happen in the next position? Position B, which we are in from 0 to 1/2. We can redraw the circuit, including only the elements that are there when the switch is in position B, and I hope this is what the circuit looks like. I hope that's what you have sketched. And now we want to know what's V sub c of t going to do during this interval. Do we know where we're starting? What's the initial value of our capacitor voltage? I just wrote that down, didn't I? Because that's V sub c of 0 minus, which is the same as V sub c of 0 plus because of the state variable nature of the capacitor voltage, and that's 0 volts. Now we want to know if we just didn't worry so much about the 1/2 upper limit, if we just said, okay, we have this circuit and we have 0 volts across the capacitor at 0, what's the capacitor voltage going to be when we get to the steady state condition without worrying about a 1/2 for an upper limit? What's a possible final value for that capacitor voltage? And here, when I'm saying possible final value, I'm saying that this actually depends on infinity or on 5 time constants, but we're not going to worry about that right now in this finding its final ultimate value. But its actual value will depend on 5 tau and when we turn the switch. But for now, let's just neglect the switch and say if we now had this circuit, what's the final value going to be for V sub c when it reaches steady state? What happens to the capacitor voltage in steady state? Does it short? Does the capacitor short? Does it open? What does it do under a constant source? It opens. So now we have essentially a voltage divider. We're dividing that 100 volts across 4 and 6, and 60% of that voltage will be across the 6 ohm resistor, and so that's what we have for our ultimate value if we didn't have to worry about a switch. Let me see if I can get some notation. Let's just say that this is V of our capacitor final 1. It's maybe not going to get there, but this is a voltage divider, so we're going to, if we could, get to 60 volts. We start at 0, and we would like to, if we just now were confronted with this circuit, we would go from 0 to 60. And if we were in a car, we would want to know how fast, right? You're going from 0 to 60, but we're not, the units are different. Here our units are volts, not miles per hour. Trying to keep us engaged here. What's the time constant for this circuit? RC. So now we need to know what's the effective resistance in this circuit. And now you get to participate. You have 4 options. Is it 4? Is that our R? Is our R 6? Is the R the parallel combination of 4 or 6, or is it the series combination of 4 and 6? Which one is it? Given that circuit, what is our effective resistance that we need to use to determine tau? Tau is RC. We ready? 1, 2, 3. Okay. So I think most of you are saying 4 and 6. Why is that the case? We want the effective resistance. Now we remove that capacitor and we look into those terminals and we say, what resistance does that capacitor see between A and B? Or if we now looked at it this way, we would say, oh, and what do I do with that 100-volt source? Open it or short it? We zero that voltage source, that's a short, so now we have this configuration staring at us if we were capacitor in this circuit. Between nodes A and B, we now have the parallel combination of 4 and 6, and what is that unit-wise or number-wise? 10? Less than 4. That's what you are thinking about. Now we have 4 times 6, 24, divided by their sum, 10. So it's 2.4 is the resistance. So now we know T effective. We actually know the first time constant in this circuit. It's 2.4. What was the resistor's value? I'm sorry, the capacitor's value? 1/2. Our first time constant that we're interested in is 1.2 seconds. And this is effective, this time constant, when our switch is in position B. That's what our time constant appears to be, or is, when we are in switch position B. So now we need to call in FIFE. And we can use FIFE because we're dealing with constant sources. And what's the structure for this? What's the final value? What did we just say it would be if we went forever? We said it would be 60 plus the initial, which was 0, minus 60, e to the minus, so we've got the FIF, now we have the exponential, which is e to the minus t. We were starting at 0, and that's over tau, which is 1.2. And you might see this written. Well, here I'm just saying let's emphasize the fact that this is position B. And now you might see somebody write this as 60 times 1 minus e to the minus t over 1.2. That's the structure of our voltage across that capacitor in position B, once we've switched from A to B. Approximately how long would it take to reach 60 volts? And here we are neglecting switching. So let's not worry yet about the switch being moved at t equal to 1/2. How long is it going to take us before we get to 60 volts? Five time constants, which in this case, our time constant was 1.2, so that gives us 6 seconds. And if we wanted to sketch this, we would have something like that. We started at 0, and in 6 seconds, that's our 5 tau. This is when we are in position B. But now we know the switch moves to position C at time 1/2. So we're not going to get to 60, are we? We're not going to see this complete shape occur between 0 and 6, because now at 1/2 something magic happens. We throw the switch, and then we end up with this circuit. And what's our time constant for this circuit? It's RC again, isn't it? Here R is 2, C is 1/2, so our tau sub 2 in this case is 1 second. Now our time constant has changed a little bit. It's reduced. And what is our initial? So now we know at 1/2 we have a new time constant. What do we do now? How do we proceed? What is the voltage at time t equal to 1/2? Or what is V sub c of 1/2? Or that's now what's our initial voltage when the switch is in position C? Again, we have audience participation. Is it 60? Is it 0? What's our capacitor voltage at 1/2? Is it 100? Or is it none of the above? Ready? 1, 2, 3. So I drew the curve before, and I actually gave you the answer, didn't I? What is the voltage at 1/2? We're trying to get to 60, but we're not quite there, are we? We're far from there. We are now, whatever we are on that exponential curve, at time t equal 1/2. And our time constant is 1.2, so we aren't even one time constant into that exponential. But we do have the formula. We do have that functional or that exponential behavior, that shape. We just have to plug in t equal to 1/2 and evaluate this, and that will give us our initial value for the capacitor voltage at time t equal to 1/2. Here it was actually none of the above. Sort of set that one up, hopefully. Now we have V sub c of 1/2 minus is the same as V sub c of 1/2 plus, which is 60 times 1 minus e to the minus 1/2 over the 1.2. Or this is now 60, 1 minus e to the minus 1 over 2.4. And if you plug in the numbers, e to the minus 1 over 2.4, that's about 66% or 0.66. All of that together ends up being roughly 1/3 of where we eventually would get to. After 1/2 of a second, we only get 1/3 of the way to that 60. And this is now our new starting position in switch position C. What's the final value of our capacitor voltage? Now this is position C. We've just determined what V sub C of 1/2 is. That's our initial position or initial value. What's the final value of V sub C? What's going to happen to the charge on that capacitor? What kind of a response is this? From chapter 7, we're dealing with two responses, natural response and step response. This is the natural response. This is basically, I'm going to discharge that capacitor through this resistor, and eventually you will end up with a final value of 0. That's now our final value. The capacitor discharges through that resistor R equal 2. Now can we use phi phi again? If we do, what's that look like? This is now V sub C of t. What's our final value? That was 0 plus the initial. It wasn't 60. We didn't have the time to get to 60. We only got part way there, a third of the way there, minus the final, times our exponential. And here we have to remember that we switched at 1/2, so we've now sort of shifted our time axis. We now are effectively sort of saying, okay, 1/2 is the initial time, or this is now t minus 1/2 divided by our time constant, which is 1. And this is what the voltage expression looks like for time t greater than 1/2. And that collapses, or a lot of that now falls away, and we now have this natural response behavior 20.44 e to the minus t minus 1/2 divided by 1. I'm not even going to show it. And that's what we have for our V sub C of t. When will V sub C equal 0 for t greater than or equal to 0? We know we started at 0, below 0. When will it eventually get back? It builds up to 20 in a half a second, and then it starts with this behavior beyond 1/2. When will we finally say, that's fine, we're done, we've reached infinity? When will that occur? When is t star? Is it 5 tau? Sort of. It's adjusted, right? It's 5 tau plus where we started that new switch position at, which was 1/2. So t star is now going to be 1/2 plus 5, our second time constant, tau sub 2. Or we now have our voltage back to 0 at 5.5 seconds. And if we now tried to sketch that, let's say this is now 20. We were up a little above 20 at 1/2. So now we were doing an exponential up to there. And then beyond that, we started exponentially decreasing. So in one time constant, which our time constant now after 1/2 is 1, at 1.5 we'll be at e to the minus 1 from 20. And what's e to the minus 1? 0.37. Now we're 37% of 20 at 1.5, which is going to be what? About 7, a little bit more. So now if I can estimate that, let's say this is now about where we're at. Does everybody understand what I'm trying to do? I'm trying to put some dots so that I can follow the dots. Bringing dots back. Now we're not mutual inductance with these dots. These are just sketching dots. Thinking, do they still have Dippin' dots or what? Is that still a thing? Now when you go to order that, whatever it is, I don't know if I've ever had that. Now you can think of all these different things we've talked about in ECE 220, right? And enjoy your dots. We do that already without even anything to ingest. Where are we next? After 2 time constants. We're at 2 beyond a half. We're at 2.5. Now we are e to the minus 2 times 20, 20.44. And e to the minus 2 is about 0.14. We're now 14%. So we're at about 3 at 2.5. And then 3 time constants, it's about 5%. So now we're down here at about 1. And at 4 time constants, we're at 2%. I can't even draw my dots that well. And then at 5.5, at 5 time constants, which in this case is 5 seconds beyond 1/2, or 5.5 seconds in total. We're down to 1% of where we started. Now can I connect the dots? That's the key. See what happens when you have dots? Makes it a little easier. And those dots were helped by the knowledge of e to the minus 1, e to the minus 2, etc., and how that partitions or percentages out your initial value. This is now what V sub c of t looks like in that ABC circuit that we started the class with. Question? So what is this picture? Is this the picture for A? Is it the picture for B? Is it the picture for C? Or is it the picture of all of them? Where were we to begin with? We were down here, right? In A. So here was A. Here was position B. And here is position C. We're trying to show all of those operating states of our RC circuit. And each of those positions we could analyze by an RC analysis. Did that answer? So we're showing the entire waveform in all 3 switch positions. Now we just need to go unbounded. For the rest of the class, let's talk about an unbounded response, or what might happen if we have negative resistance in an RC circuit. Here's a circuit that's been cooked up, and let's now say that we have a dependent source and we want to find the capacitor voltage, assuming we initialize that capacitor at 1 volt at time 0. What's going to happen beyond time 0? We want to know what's the behavior of that capacitor voltage based on this circuit. What kind of a behavior would you expect this to present? Do you see any independent source? There's no constant source, so you're not thinking anything like a step response behavior. You're saying, okay, well, I have a dependent source. Oh, great. Now what do I do? Well, supposedly this is now in chapter 7, so we must be dealing with RC circuits. Is there an effective resistance that that capacitor sees? And can we find it? Now what we're trying to do is look back or to the left from the capacitor's terminals and say, what's the effective resistance I see as the capacitor? What do I see? So let's just redraw that circuit. We now have we want to know, what does that circuit from terminals A and B look like? This was 4, this was 2, and this actually defined our dependent variable I sub 1, and this dependent source was a dependent current source of 6 I sub 1. How do we find R effective? This is a review for the final. How do we find the effective resistance looking into terminals A, B? Do we set our sources to 0? Our independent sources are already eliminated. We didn't have any, so we don't need to do that. How do we find the effective resistance? We have to do a test source, don't we? All right, let's do a test source. Now we only have a dependent source. And it really may just depend on your mood which one you apply, but you have to apply a voltage, a known voltage, or a known current source. Today I'm just going to apply a known voltage test source. So let's now apply a voltage test source. And we could fix it at 1 volt. We could even leave it adjustable as V sub t, whatever you feel in the mood to do. This is kind of nice. It just depends on my mood, how I'm going to solve this. So once we apply that voltage source to those terminals, then what do? We have to find the current coming out of that voltage source. We find I sub t, and once we've done that, now we can compute the effective resistance by forming the ratio of that voltage that we applied, that known voltage, and putting that over the current, the test current coming out of that source. So here we're just going to draw it again. I'm actually buying myself time. I'm trying to think how we can solve this. So if I just keep drawing this circuit, I'm hoping some magic happens and I'll be able to solve it. So here's our test voltage. This was now 6I1. This was 2. Here's I1, and this is 4. And we are actually trying to find I sub t either as a function of V sub t or V sub t equal to 1 volt. If we fix V sub t of 1 volt, then we'll get a number value for I sub t, and we can form that ratio to find R effective. How are we going to analyze this circuit? I know one response, mesh analysis, right? Nah, let's not do mesh analysis. Let's write a KVL. I'm sorry, misspoke, a KCL. I was thinking node voltage and I wanted to say KCL and I blended them. I need to do a KCL. So now we're writing KCL at, everything's in parallel, so that means we really just have to write one equation. We're going to write a KCL here. I have I sub t coming in, and everything else I'm just going to say is going out. I have I1 going out. Well, I have minus 6I1 going out. And then I have Vt over 4 going down. And now I have all sorts of variables. But where those come from, I hope, is clear. KCL now, I have in is I sub t, and out is I1 on the left. In the middle, I have minus 6I1 out of that node, and I have Vt over 4 out. I need to get rid of some of that. I need I sub t in terms of V sub t, or I could replace V sub t with 1 and keep going, but can we find a relationship between I sub t, V sub t, and I sub 1 so that I can get rid of I sub 1? Yeah, we're putting V sub t voltage across that parallel combination. We can find I1 by Ohm's law. I sub 1 is now V sub t over 2. Now if we use that, now we know that I sub t is equal to V sub t over 2 minus 6 V sub t over 2 plus V sub t over 4. And now we have what we want. We have one equation that contains I sub t in terms of V sub t. We have 1/2 minus 3 plus 1/4 times V sub t. Or I now have I sub t is minus 9 over 4 V sub t. I could plug in V sub t equal to 1, or I can just leave it alone. I know my R effective is now my applied voltage V sub t over the measured current out of that source, and I have that source I sub t current in terms of V sub t. And now, because I had that dependent source playing mind games with me, now I have a negative resistance. I now have R effective as minus 4/9. Or my effective circuit and what was C? I think I made that to be a convenient 9 farads. Did I even label that before? Yes. So initially I said it's 9 farads. Now we're trying to solve this circuit. And now we have an RC circuit, but we have a negative resistor. We need to kind of step back and say, wait a minute, this is a little bit not like what we've had up to this point. Let's just solve this from the beginning. Let's just write a KCL at that node. And now we know we have V sub C over R, which is minus 4/9, plus, what's the current down there on the right? It's kind of cold in here. That was a hint. You can use ice to find that current. You know it's now C dV sub C dt, and that's equal to 0. Or we can now say that C dV sub C dt is equal to, clearing the fraction, or getting that fraction out of the denominator by multiplying top and bottom by 9/4. We end up with that, and this was actually 9. Those 9's cancel, and we're left with dV sub C dt is equal to 1/4 V sub C of t. We're now trying to find an answer, a V sub C of t, that satisfies that differential equation. That's the governing differential equation for this new negative resistance RC circuit. It's now we have the time rate of change of that voltage is 1/4 of that voltage. What shape or structure of what function structure gives us the same thing when we differentiate it? An exponential. So now let's just speculate that V sub C of t is some a e to the 1/4 t. We know if we differentiate e to the 1/4 t, that 1/4 will pop out and give us what we want, knowing our calculus. So this is now the structure of our homogeneous solution. And what do we know? Do we know anything more? A is an unknown. Can we find it? Capital A is an unknown voltage. We have the exponent, and this exponent should be making us a little bit nervous because there's no minus sign. Now as we plug in bigger values of t, what's happening? We have an exponential growth. And that's from what? Having that negative resistor. It's now not dissipating energy, it's now helping things grow. And A we can find given the initial value that we were given for that capacitor's voltage. We said we're starting it at 1 volt. That was a given piece of data. We were given that V sub C of 0 was 1 volt. And now we know the structure of V sub C of t. Let's evaluate it at 0 and set it equal to 1. Now we know what A is. A is 1. Or we now know that V sub C of t is equal to e to the 1/4 t. That positive exponent now says we have exponential growth of that capacitor voltage. What happens now if you connected this up in the lab? You guys always wear closed-toed shoes and safety glasses, right? Because it might come in handy here. What might happen now if you built this circuit and established the initial voltage of 1 volt on that capacitor at time 0? And then you set your stopwatch and watched it. What's going to happen? V sub C of t. Is it going to be like one of those fireworks and you light it and it just grows? It might be fireworks, actually. It might explode. The capacitors usually have a voltage rating. Let's say that somebody said, you know what? I think this capacitor had a voltage rating of 100 volts. Do you know when it's going to reach 100 volts? If somebody plugs that in, can you turn the switch off before it explodes? When do you have to turn the switch off? Can you find when it explodes? When does V sub c of t equal or pass through? Let me just say, when is V sub c of t 100 volts? It's not going to stop there. It's going to be zipping exponentially through 100 volts based on this expression, e to the 1/4 t. Well, there we can simply evaluate that. We can say V sub c at t, we'll call it a star, is e to the 1/4 t star equaling 100. And you can solve that for t star. Take the natural log of both sides. You now have 1/4. I'm going a little long. If you need to leave, I'm not going to be too upset. No, I won't be upset. Natural log of 100. We now know that t star, this now tells us how much time we have before we reach over and turn the switch. 18 seconds. That's before it might do some harm. That's why we have our safety glasses. We'll pick up at chapter 8 after we've recovered from these unbounded responses.